redshift 15 sources.
No, I mean, yeah, yes, what you're saying.
Right. The problem is that if you're looking for, the problem is basically if you're looking for the first galaxies with JWST, we need some hints as to where to find them. And that's kind of going to be the problem. So I think the point is that we've ended up with now these two potentially sharp problems. One is that we have this main sequence that's telling us that despite these many different kinds of initial conditions in different environments, galaxies all grow the same way. And the second are these hints that we have maybe very massive, but certainly very, very luminous galaxies that are more luminous than we might have thought you would be able to make at high redshift, and we don't know why. Sorry, yeah?
So one more thought on this. So the highest redshift galaxies we found with Hubble or was something about 10.
Yeah, there are a few redshift 10 detections.
The physical time between redshift 15 and redshift 10 is tiny.
Yeah.
So you could expect that maybe the structure that you're looking at, large-scale structure, is actually really correlated. So wouldn't it make sense to look next to redshift 10 galaxy, redshift 15 galaxy?
The problem is that that's still going to physically be a fairly large distance, though.
Fair.
Right? In other words, the problem is you kind of ask what a reasonable correlation length is at that redshift.
Exactly. That's the question. So, like, well, how does the physical distance from the equals 15 to 10? I have no idea what that is. How does that correspond to the structures that have collapsed?
Well, it's going to, well, yeah. So it's going to be a couple hundred million years, I think. So that still is going to be an enormous distance along the same line of sight. Okay, so what I wanted to do in the remaining time was to kind of quickly throw a toy model that we've been playing with at you that potentially can shed some light onto these, or maybe what you'll be able to do is tell me a reason that it's silly and we shouldn't be thinking about it. Because we're sort of just playing around with this and trying to figure out whether it's worth going further. So part of what we've been playing around with here is thinking about a little bit more about the stellar initial mass function and what happens at different temperatures. And we wrote a paper last year trying to calculate what happens in this fragmentation process as we change the temperature. And in particular, finding that on the high mass end, really nothing's changing in the slope of the IMF. Okay. But as you get sort of solar mass and below, now you start to be able to make fewer of the low mass stars at high temperature. In other words, it's probably more fair to call this a bottom light IMF than a top heavy IMF, even though in many ways they'll behave similarly as far as things like mass to light ratios. And this initially becomes important at high redshift simply because in the Milky Way, where we're trying to measure the IMF, we're typically measuring this at around 20 Kelvin. But once you get above a redshift of about 6, the CMB temperature is above 20 Kelvin. So if we're looking at a redshift 8 galaxy, we already know the temperatures ought to be something above 20 Kelvin, even just from the CMB. And then there are potentially other effects related to star formation that will increase the temperature as well. So this was kind of one piece of what we're doing. And then the other idea is, well, look, we want some sort of strong feedback loop that's going to drive star formation to the same track. What if we think about this in the case where the temperature is actually being dictated by the star formation? And we want something that's not going to just be local to massive stars, but is going to actually dictate temperature throughout the entire galaxy. And so that means that the natural culprit is to look at cosmic rays. They're produced in the explosions of very massive stars, but they have a long enough mean free path that they actually end up heating the entire galaxy reasonably close to uniformly. So at least as a toy model, we can kind of treat a galaxy as having one sort of cosmic ray source with one temperature and play around with this and ask what happens. So imagine the case in which a galaxy is entirely dominated by cosmic rays. And then the idea is that maybe you can produce some kind of feedback loop where as you increase the star formation rate, you end up changing the IMF and changing the star, changing the IMF, changing how many cosmic rays you get back out, and this produces some kind of feedback where that temperature then drives the behavior of the system. Okay? So one way to think about it is imagine that you increase the temperature from a galaxy that was otherwise near some equilibrium. Okay? Is it really in equilibrium? Do you kind of come back to the same state? Okay? Well, when I increase temperature, two things are going to happen simultaneously. The first is the star formation rate's going to go down. that even if we think about this just from a Jeans mass point of view, what happens is an increase in temperature means more thermodynamics. Trying to expand the gas means I need more gravity to collapse it. And so therefore the star formation rate goes down because fewer clouds collapse, and the ones that do collapse maybe collapse a little more slowly. Okay. At the same time though, the IMF is becoming bottom lighter, and so I'm generating more new cosmic rays per unit SFR. And what we really care about is the combination of these two, right? So that somehow this is going to drive a temperature change. But what we really care about is kind of what this combination is, and it turns out that several different solutions are possible to this equation. Okay, so one of the solutions, right? One of the solutions is essentially that this SFR wins, and you get a decrease in cosmic rays. You know, that the decrease in SFR is more important. Okay, and that is going to drive the temperature back down, and so we get some sort of attractor solution, right? And this is the one that, if we're really optimistic, we might hope is going to look something like the star-forming main sequence we're trying to explain. Okay. So we went and just solved these equations, and it turns out the answer is that it might. So it's actually a little bit more complicated, because I wanted to give you a situation in which the temperature is being dominated by these cosmic rays, right? But if we actually go ahead and think about what a galaxy is going to do, there are several components of temperature that we have to consider. Okay, so there's a cosmic ray temperature. Now this starts very low because we started it kind of with 0 stars. I should mention this does not mean that there's 0 star formation rate here, right? There's actually a very high star formation rate with the initial conditions we gave it. The reason that there's initially very low cosmic ray contribution to temperature is simply because stars take a little while after you form them to explode, right? And so even if you start with a very high star formation rate, there's some lag time before the cosmic rays that you generate actually really start to ramp up and heat the galaxy. Okay, but the point is there's some cosmic ray contribution, and at some redshift range it's going to dominate, but there are other things that can dominate as well. At very high temperature, it's actually CMB dominated. And this turns out to be quite useful, because I mentioned earlier that one of the properties of the star-forming main sequence that was a little puzzling is that the relevant unit of time was cosmic epoch. That galaxies that assembled at different times still have the same star-forming main sequence at a given redshift. Well, this maybe provides a mechanism for doing that, because you sort of have this burn-in phase where you're CMB dominated. You're only making massive stars because the CMB keeps you at a high redshift. And so the ones that assemble earlier will also only make massive stars. So they'll make massive stars, those stars will explode, they'll be a little bit dustier and a little bit more metal rich than the ones that assemble later. But they'll otherwise actually end up with very similar initial conditions. Because if the star-forming main sequence is kind of coming from this phase, what triggers the start of the star-forming main sequence now is not the assembly time, but rather the point at which the CMB temperature drops enough that star formation can take over and drive you to this equilibrium. So it maybe gives you a mechanism for that. Then we have a period of time in which the star formation is dominating. And then actually at late times, as we use up most of the gas, now actually, like in the Milky Way, the cosmic rays don't dominate the temperature anymore, right? In the Milky Way, the cosmic rays alone would drive it to about 5 Kelvin. But other effects from having low mass stars and their heating keep it at more like 20. Yeah?
Are the temperatures really oscillating at late times, or is that numerical stuff?
That's probably numerical, yeah. So it's probably not actually oscillating, but there's some kind of feedback in there. And the other thing to consider is that all of the short-term dynamics of this are going to be just dead wrong, because we've intentionally kind of picked a very simple model where it's one kind of state machine, there's one temperature for the entire galaxy instead of, and it's entirely uniform. We really just kind of wanted to play with what the solutions to these equations look like. And the right way to do this is going to be to include not just this, but all the other effects in a proper simulation. So the idea is we kind of get these 3 phases. Okay? Now all of our observations really are only going to look at this very late time. right? This is the only thing we can observe. And what's happening here is that basically temperatures kind of gradually drop along this attractor solution that we get. And we can sort of measure this. So we can't measure gas temperatures, but there are measurements of dust temperatures and kind of what this looks like along the star-forming main sequence. So here are some different redshift ranges. The dashed line for each of these is kind of where the star-forming main sequence lies. And what we see is that at least if we look at dust temperatures, it is the case that there's some temperature gradient, and when you're above the star-forming main sequence, you're quickly going up in temperature and so forth, that you might think would drive you back toward this equilibrium answer, right? It is the case that the main sequence is roughly running along a line of constant temperature, and that temperature even does have kind of this redshift dependence, whereas we go toward late times, it's declining a little bit. A bunch of things, there are a lot of caveats that I should give you about a picture like this, right? One is, on the prediction side, it's not fair to say that we predict these temperatures. We predict qualitatively that you're going to get an attractor solution and that the temperature is going to be declining with time. But everything quantitatively depends upon things that we're allowed to tune with the gas inflow. So it's much more fair to say that a model like this can match predictions than that it can match observations than that it can predict them. Right? It's really making qualitative predictions that are robust, but then matching. Okay? The other is that not only are these dust temperatures instead of gas temperatures that I'm showing you, but these measurements are luminosity averaged dust temperatures, right? Because that's what we can get at. And the problem with the luminosity average is that because luminosity goes as t to the fourth, these aren't really telling you about the coldest